We move on from polynomial functions to exponential functions. This is a class of functions that gets used a lot in the real world. Applications are population growth, compound interest, radioactive decay, and many others. The idea here, okay, well, exponential function, the variable is going to be an exponent. So a model for the types of exponential functions we'll look at in this part, something like f of x equal to 2 of x. So the idea here, you pick your favorite number, you're going to take 2 to that number. Now, whenever we have a new function, okay, we want to try some numbers out just to get a feel for it. If we can get enough numbers, we can make a graph. So let's take a look. Well, if we start with whole numbers, so if I put 0 in, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2, 2 squared is 4, 2 cubed would be an 8, and so we see as we go in the positive direction, these numbers are getting bigger and bigger kind of fast. In the other direction, okay, if we put in a -1, well, 2 to the -1, that says flip it over, we get a half or a 0.5. 2 to the -2, we flip it over, that's a 1 over 2 squared or a fourth, 0.25. 2 to the -3, we flip it over, that's a 1 over 8 or a 0.125. And so we see as we get bigger and bigger negative numbers, okay, in magnitude, what's going to come out is going to get smaller and smaller because the denominator will get bigger and bigger. So as we get more and more negative, values for 2 to the x are going to get driven down to 0, but they're never actually going to get there. So if we were to connect the dots, this is what the graph of 2 to the x looks like. As I go to the right in the positive direction, it's going to spike up really fast. As we go to the left in the negative direction, this is going to go down to 0, but never quite get there. Now, big question, does it make sense to connect these dots? Well, remember, we could take exponents to any rational power. So if I wanted 2 to the 1/2, not a problem if I know how to work with radicals. So 2 to the 1/2 is a square root of 2, and if I'm just interested in getting a rough picture, we can let that be 1.4. Put that on the graph. Or, for something a little bit more complicated, we could take 2 to the 4/3. Remember, how does this work? Well, different ways we can look at it. Say for here, what I'll do is I'll put the 1/3 on the inside, the 4 on the outside. So what we're doing is we're going to take the cube root of 2 and then raise that to the 4th power. Now, this is a calculator exercise. So what we get out of here is going to be 2.520 roughly. And that's about 1/3. And that looks about right on the graph also. So that takes care of whole numbers, negative numbers, rational numbers. Every real number is close to another rational number, so that's going to be enough to get all real numbers. For irrational numbers, like say square root of 2 or pi, well, for us, good enough just to go to a calculator. You'll approximate your irrational number, so the answer that comes out is going to be an approximation anyway. So, for instance, if I want 2 to the square root of 2, well, I could put in 2 and then 1.414, however many decimals you want. If we cut this down to just 3 decimal places, we get a 2.665. If I take 2 to the pi, same idea. We go 2 to 3.141 and just chop it off at as many decimals as we need. And then that'll be roughly 8.825. So note, pi is a little bit more than 3. So 2 cubed is 8. So we expect 2 to the pi to be a little bit bigger than 8 also. Now, as I noted, 2 to the x is going to be the model for all exponentials if the base that we're using, the a, is greater than 1. So if we have this a greater than 1, then you can pretty much get the whole behavior of the graph of your exponential by plotting 3 points, -1, 0, and 1. A to the -1 is just flip a over. If a is bigger than 1, then 1 over a is going to be between 0 and 1. If I put in 0, doesn't matter what a is, it's going to go to 1. And then if I put a 1 in, we're just going to get a itself. And then if you want more detail, you could try something like over here, but you're going to get the same exact shape. Okay, so as you go in the positive direction, it spikes up. As you come to the left, it's going to come down and flatten out at 0. Now, with this picture, a couple things to note. The domain is going to be all real numbers. We just kind of explained how you can define exponentials at every real number. If you can get them at every rational, then you can approximate them for every irrational also. Then from the picture here, I can get the range. Okay, we know, well, where the y values start. If I come up from the bottom, they're going to start at 0 and then go all the way up. And then note, we're never actually getting the 0, so I would use parentheses. Really important thing to note here, easy to overlook. If I take a to any number, that's always going to be a positive number, even if you put in a negative exponent. So be careful with that. Next, we'll consider exponential functions with simple expressions in the exponent. For instance, let's try 3 to the x and 3 to the x plus 1. If we compare their graphs, okay, so for 3 to the x, what are we going to do? I'll take the points -1, 0, and 1 as noted. We'll get a 1/3, a 1, and a 3 coming out. I plot those points, and we get this exponential graph along the bottom. For 3 to the x plus 1, now recall, what do we do with the x plus 1? Well, we just follow the x. So I'm going to put our numbers in, say -1, 0, and 1 in for x. Then we compute x plus 1. Then we compute 3 to the x plus 1. So if we put -1, 0, and 1 in x plus 1, we'll get 0, 1, and 2. Those are the new exponents. So we'll get out 1, 3, and 9. If we plot these points, this has the same basic shape as an exponential function. Okay, you'll note it goes through 3 instead. But what's happening here? What's the relation between the two? Well, if I take 3 to the x plus 1, product rule for exponents says we could split the exponent 3 to the 1 times 3 to the x. So I'm just taking 3 to the x and multiplying by 3. Now, 3 to the x, if we think of those as y values, then if I multiply by 3, we're multiplying all y values by 3. So what we're doing is stretching the graph along the y-axis by a factor of 3. For comparison, let's put a number outside of the 3 to the x. So let's take a g to the x equal to 3 to the x minus 2. Same idea. We'll just take a bunch of points. Here I'll take -1, 0, 1. I'll throw in a 2. And then we'll just plot points and see where things go. So here, okay, note there's nothing to be computed in the exponent. We just put our numbers in and then subtract 2. So that's what we do following the x. And what comes out? -1, 0, 1, 2. Out comes -1, 6, 6, 7, -1, 1, 7. If we take a look at the graphs, okay, close to this, what are we doing? You'll notice here, okay, if things are drawn to scale, then the 3 to the x, which is on top, all we're doing here is dropping by 2. Okay, if I take 3 to the x, subtract 2, that says you're taking all the y values from the previous one, taking 2 off, or you're going down by 2. And so we see the relation between the graphs is just drop by 2. In the higher math, say calculus, and the sciences, we pay special attention to what we call the natural exponential function. So this would be f of x equal to e to the x. E is a special number. We call this the natural base. And that's roughly 2.71828. And then that goes on forever like pi. Now, why e is special? Like I said, that's something for calculus. We'll try to give an indication of how e arises at the end of this. Now, e it really is special enough that it deserves its own letter. Okay, so that goes along with pi. Phi, the golden mean, so that's roughly 1.61803, and then that goes on forever. This you might see if you stick around in math. And then we also have I, which is the square root of -1. Now, for some examples using e to the x, let's try a population growth scenario. So let's suppose we have a bacteria population, okay, a colony, that's going to grow according to the rule 100 e to the t, where t is measuring time in weeks. Okay, and then when we use these exponentials, you might hear the term exponential growth. What we want to know, first, I just want to know how the population grows by checking at 0 weeks, 1, 2, and 2.5 weeks. So this is just going to be substitutions. And then I want to do the problem backwards. I want to know how we're going to get to, how long does it take to get to 10,000? So for the first one, we could just set up a table. I'll have for t, our time, 0, 1, 2, 2.5. And then we're just going to substitute each time into our function, evaluate with a calculator. So for 0, we'll put in e to the 0, which is a 1. Anything to a 0 is a 1. Doesn't matter if it's something strange like e. Multiply by 100, we get 100. T equals 0 is where we start, and that agrees with the original population of 100. For t equals 1, we substitute. E is roughly 2.71828. Multiplied by 100, we round to 272. So this is definitely increasing. We put in a 2, it's going to be e squared. Multiply by 100, we get 739. And then for 2.5, e to the 2.5, multiply by 100, we get 1,218. So we see as time goes on, this is definitely growing. Now, for the reverse problem, well, what I can do, right now it's just going to be guesswork. Okay, we don't have a good method for solving for an exponent. That's going to be where we introduce logarithms coming up. What can we do? Well, I could follow out the pattern here, and I'll note when I get to 4, okay, we'll have 5,460 members in our bacteria colony. If I go to 5, I'll get 14,841. So 10,000 somewhere in the middle there. If I try 4.5, we get about 9,000. And then I could just keep playing this game until I narrow it down. When I'll wind up with 4.61 is going to get us to the 10,000, a little bit more that we were looking for. Better way to get that 4.61, or how I actually got that 4.61, that's going to be logarithms. So coming up eventually. For our last major application, we have compound interest. Now, we've gone through the mechanics of compound interest at the end of video 8.1a. Let's go over it really quick. So the scenario is, say I go to a bank, I deposit $1,000, I have an agreement with the bank that they'll give me, say, 10% annual interest at the end of the year. So what that means is the bank is going to pay me money on top of the money they're holding for the right to borrow my money, and then they can do whatever they want with it. If I let that money collect year to year, so I would have, say, at 10%, at the end of 1 year I'd have 1,100, 1,000 plus 100. If I let that roll for another year, I'll get 10% on top of that 1,100, and we could keep doing that over and over again. So with compound interest, you get interest not just on the money you're lending, but on the interest of the interest, and that keeps piling up. Now, what are the parts here? We have the initial amount we're lending, we'll call that P. T is just going to measure time in years. R, the interest rate, that's going to be a percentage. We make it something we can work with in the formula by dividing by 100. The model for the formula is, as you go from year to year, you multiply by a factor of 1 plus r. So after t years, you're going to multiply by t 1 plus r's, or 1 plus r to the t, and then that's where the formula comes from. Now, this formula really doesn't reflect what happens when we put money in the bank. Maybe more if you work in the money market or bonds or things like that, which can have 20 or 30-year periods. What's going to be more realistic would be something where maybe I get my interest twice a year. So we call that semi-annual. Or if I get my interest every month, call that monthly. You could even have it so that you get interest throughout the day. How does this model work? How does it change our initial one? Fortunately, not by much. So if we call n the number of times we collect interest, the number of compounding periods in a year. So for semi-annual, we'd collect 2 times a year. For monthly, we collect 12 times a year. I call that n, and then the changes to the formula are going to be, for the r, we divide by n. So for instance, for semi-annual, if I've got 10% for the year and I've got 2 compounding periods, the way the banks work it, they'll give you 5% for each period that you leave it in. Likewise, for the monthly, I would take whatever the 10% say, spread it out over 12 periods, so I would divide by 12. That's the interest. For the exponent, what the exponent's measuring is the number of times you collect interest. So if I collect interest n times in a year, then in t years, it's going to be t times n times that we collect interest. So that's now going to be the new exponent. And then that's our new formula when we change up how many times you collect interest in a year. Let's look at an example. So let's suppose initial amount's 1,000. We'll have annual interest equal to 12%, so the numbers are easy. We divide by 100 to get our r equal to 0.12. Let's compare what happens at the end of 1 year. Now, with just collecting interest at the end of the year, okay, we just use the 0.12. That'll give us $1,120. If we do semi-annual, so I'll collect interest every 6 months. Now we're going to split the 12 by 2, so that'll go to a 6% for a 0.06. And we're going to compute interest twice throughout the year. That's going to give me a $1,124, so it looks like a slightly better deal. If I go to 12 for the monthly, okay, what are we going to have? We'll have now interest is spread over 12 months, so we're going to divide by 12. That'll give us a 1% per month, so we'll have a 1.01. I have 12 compounding periods in a year now, so we raised it to 12. That's going to give us a 1,127. Still looking better than what we had going semi-annual. The question is, do we have a money machine here? Can I get this, say, collecting interest down to the day, the hour, the second? Can I make it so that I can make as much money as I want? The answer is going to be no. And what happens, we see that E is going to come back into the picture. Okay, and so for the next board, we call this continuous compounding. The formula is going to be, you're just going to take for the factors from before, E to your interest rate, so it's E to the 0.12 in this case, multiply by your initial amount, and then here we get 1,128. That's going to be the ceiling on how much money you can make. So you'll note it gets better, keeps getting better, but even at 12, it's not getting as good as it was before, stopping at 1,128. To be complete, here's our formula for continuous compounding. So this is going to be compounding, say, down to the second. We have our initial amount P. We have T represents the amount of time that passes in years. And our factor now is going to be E to the R. R is our interest rate. If it's a percent, we divide by 100. E, of course, is our natural base. That's going to be 2.71828, going on forever. Now, why should this model have anything to do with E or exponential growth in general? Let's take a look. So we're going to use our model for compound interest, but we're going to set some numbers and see what happens. So I'm going to let the interest rate be 100%, so R will be equal to 1. Time period, we're just going to consider what happens in 1 year. Then we're going to let the number of compounding periods go to infinity. So the idea is we're going from once a year to twice a year to 3 times a year to monthly 12 times to daily 360 times, all the way down to the second. Let's take a look at what happens. So this is just going to be numerical. Now, with those assumptions, our formula is going to be, okay, there's, say, $1 initial amount, 1 plus 1 over n. Okay, we're taking our interest rate of 1, dividing by n, and then we're going to raise to the nth power, because we're just doing 1 year. Number of compounding periods in a year is now going to be n. If we just do annual interest, so we just compound at the end of the year, we're going to get a 2. If I do it 10 times in a year, okay, the interest rate is going to become a 0.1 for each period. We're going to compound interest 10 times. I work it out. We get 2.5937. So it's growing. 20 times, 1 over 20 is a 0.05. 1.05 to the 20, we get 2.6533. 100 times, we get 2.7048. 10,000 times, we get 2.71814, and we see the decimal starting to come out. You go to 1 million, 100 million. As you do this, it's going to get more and more precise, and it's going to converge to this number E that we've been talking about before. And so that's how we get E, by this process that we call limiting.